All right, so we are now ready to move on to the next session. And it is my pleasure to introduce the next 6 speakers who will be presenting quick lightning talks. And as a head up, all this research will also be presented during the poster session. So there will be an opportunity to hear more and interact with the speaker. And the first speaker is Angelique Taylor. She is a PhD candidate in computer science and engineering at the University of San Diego, California. Angelique?
Good morning and thank you. Hello everyone, my name is Anjali Taylor and I work in the healthcare robotics lab under the supervision of Dr. Lowell Rick. Our lab explores human robot teaming in safety critical complex environments, including hospitals, homes, and work sites. My work focuses on problems that robots encounter in human robot teaming, such as robot perception of groups of people, interaction among groups, and navigation among groups. Today, I'll talk about my most recent work on designing navigation systems for mobile robots in safety critical settings. The emergency department is a high stress, fast paced, safety critical environment, which is frequently overcrowded, understaffed, and underfunded, all of which have become worse during the COVID-19 pandemic. To alleviate these challenges, I designed a social navigation system that enables robots to fetch and deliver supplies to emergency department staff workers. However, to enable robots to work in these environments, they need to understand the severity of a patient's condition in order to make intelligent navigation decisions. For example, if a robot observes a patient having a heart attack, it should avoid navigating near this patient as it might interrupt patient care. To address this challenge, I developed a system called the Safety Critical DQ Network, or SafeDQN. SafeDQN enables robots to consider the severity of a patient's condition, or their acuity, and use that information to navigate in a manner that prevents them from interrupting patient care. We estimate the acuity of patients from video data using 2 intuitions. The first intuition is that high acuity patients tend to require fast, precise treatment, which ultimately results in very dynamic motion by the emergency department staff workers. Second, high acuity patients tend to require treatment from more emergency department workers than low acuity patients. I designed a reinforcement learning system that perceives patients, the emergency department workers, and the relative motion of those workers as they treat a patient to infer the severity of the patient's condition. Then SafeDQN encodes this information into a neural network to navigate such that it can avoid areas of high acute patients. We experimentally shown that SafeDQN is able to effectively avoid areas of high acuity patients and is comparable to classic navigation methods. The key strength of SafeDQN is that it visually infers the context of patient acuity, while comparative methods do not. In the future, we plan to deploy SafeDQN on a physical robot at a medical simulation training center here at UCSD to evaluate the effectiveness of the system in real-world settings. To the best of our knowledge, this is the first work that designs robots for safety critical settings while considering the severity of patient conditions. We hope our work inspires robotics researchers to design robots to work in safety critical settings and ultimately help improve patient outcomes. I would like to give a special thanks to my advisor and sponsors of my PhD research, and I'd be happy to take any questions.
Thank you, Angelique. Our next speaker is Shinko Ni. She is a PhD student in computer science at Stanford University. Xinkun?
Good morning, everybody. Thanks a lot for having me here. The title of my talk today is Learning When to Treat Policies. Let's start with a motivating example. This doctor checks on the patient from time to time to decide when is the best timing to take the ventilator off of the patient, so the patient can breathe on their own. And in this problem setup, the covariates are the patient's health state, the blood pressure, and they evolve over time. And based off of the time-varying covariates, the doctor needs to dynamically decide if it's the right time to take the ventilator off and can only take an action once. So if the doctor took the ventilator off too early or too late, there will be medical consequences. So the question is, can we learn from observational data collected in the past to inform the doctor when is the best timing to take the ventilator off? Our goal is to do sequential policy learning in a given structured policy class for learning when to start or stop policies. As an example of such a policy class, we can consider all linear thresholding policies. Here, we always start with the treatment on and stop the treatment as soon as some health metric goes above this black solid line. In this case, this black solid line represents the treatment policy. We want to learn what's the best line to draw to maximize some outcome of interest. Conceptually, our proposal is able to decompose this sequential policy learning problem into a series of single-step treatment effect estimation problem that leverages the recent advances in causal inference. There has been significant recent progress in this area, and I'm including 3 methods here for comparison: importance weighting, fit-acute iteration, the doubly robust estimator. Compared to existing methods, just like the doubly robust estimator, our method is able to have robustness type properties for policy evaluation. Unlike the doubly robust estimator, which learns separate value functions for every policy in a policy class, which make it hard to scale computationally, our proposal learns universal value functions shared across all policies, making it an attractive alternative computationally. Unlike fit-acute iteration, which learns optimal policy without a predefined policy class, we can work within a predefined policy class that provides more interpretability. Finally, we provide the first root and regret band in the sequential policy learning setting with unknown propensities. Our proposal is called the Advantage Doubly Robust Estimator, or ADR, and it empirically achieves good performance in terms of regret in policy learning in our simulations, and it doesn't require Markovian assumptions. I will also present this work in more detail at the poster session, and I hope to see you there.
Thank you, Xinkun. Our next speaker is Niranjani Prasad. She recently completed her PhD in computer science at Princeton University, and she is now a senior researcher at Microsoft Research Cambridge in the United Kingdom. Niranjan?
Cool. Thank you for the introduction. Hi, everyone. I'm Niranjani, and I'll be talking about today about my work on defining admissible rewards for reinforcement learning in clinical settings. So this is work I did while in Princeton in collaboration with Barbara Engelhardt and Sonali Barbu. So reinforcement learning with Markov decision processes has been seen in recent years as, and at the center of RL is the assumption that this feedback or reward function is the most fundamental definition of the task at hand. However, designing a scalar reward function can often be challenging in practice, as feedback is received over various timescales and can represent clinical implications that must be with very different priorities that must be traded off. The last talk gave the perfect initial motivating example that I'll continue. Consider the problem of weaning or taking a patient off invasive mechanical ventilation in the ICU. Both premature and delayed weaning are associated with worse outcomes for the patient. And it's essential to, when managing ventilation, to maintain the immediate physiological comfort and stability of the patient over the course of the admission. So how then do we weight these various objectives to obtain a single scalar reward function that reflects what patient histories can tell us implicitly about what is reasonable behavior for this task and allow us to learn a policy that we can trust? So what I do to tackle this, what we do here is draw from literature on inverse reinforcement learning to assume that the reward R can be written as a linear combination W times phi, where phi is a vector function of state features. We can then write our optimal policy pi, which maximizes this expected cumulative reward as a linear function of these reward weights W. What we then want to learn is for what convex combinations of these reward components can we learn policies that are, one, consistent in that they do not diverge too far from observed behavior in their value, and evaluable with high confidence performance guarantees. And this is given that we only have a set of past trajectories collected from flawed but presumably safe expert behavior. So what we do in this work is show how we can formulate each of these conditions as linear constraints that form polytopes in the space of reward weights W. The set of admissible reward weights that we want to choose from is then simply those that satisfy both sets of criteria. To see what this admissible set looks like for the ventilator weaning task, we can formulate the reward as a linear function of 3 penalties on ventilation, abnormal vitals, and reintubation. And if we sweep across the 3D space of weights and evaluate each weight vector according to our consistency and evaluability criteria, we find that the set of admissible weights tends to favor high importance on the vitals penalty, which basically has the effect of favoring policies that are relatively conservative in weaning patients, reflecting what we expect to see in the patient histories. So if we choose a reward function from this space, we can then learn a policy that's anchored relatively close to this conservative behavior in the historical data. So we described this in a few other settings, but I'll stop there for now. And thank you all for listening, and happy to discuss further at the poster session.
Thank you, Niranjani. Our next speaker is Sonali Barbu. She is a postdoctoral fellow in computer science at Harvard University. Sonali?
Hi, everyone. So can you see the screen? I hope you can. Today, I'll be talking about estimating treatment effects from well-curated populations to less resourced populations with HIV. And I'm Sonali Barbu, and this is joint work with Mario Visa, Volker Rath, and Finali Doshi-Velez. So HIV is currently a virus that's highly mutagenic and affects 36 million people worldwide. To understand how the virus actually mutates and evolves, we typically rely on genomic sequencing, which we can then determine or use to determine how to treat individuals. So if an individual has certain mutations, we know that we don't treat the patient with drugs that would essentially cause those mutations. And this has been successful in many parts of the world, such as in parts of Europe and in America and overseas as well, where sequencing technologies are highly prevalent. However, in populations that are less resourced, we still don't have access to this NGS kind of technology. And so this remains a problem. So the question that we ask here is, can we sort of use the relevant information that we gain from these well-curated populations to reason about treatment effects in these less resourced communities in Africa? The approach we present here is based on a local and transfer mixture of experts framework. We first learn a transfer expert based on a deep information bottleneck principle that identifies relevant information to transfer between the different populations to reason about treatment effects. If no such transfer is possible, we fall back on a local expert strategy to treat the individual. Finally, we have a gating network that determines when such a transfer is possible. So our key aspects are identifying what to transfer and when to transfer. Overall, we find that by doing this mixture of experts approach, we are able to adjust for certain kinds of confounding, and overall, our approach outperforms existing baselines in terms of optimizing long-term patient outcomes as an immune response. So locally trained baselines perform worse than current practice, while transfer baselines basically barely reach current practice, and combining the two basically leads to the highest rewards. More importantly, our method is able to identify exactly what information is relevant to transfer between these populations if we can. So particularly, the subtype information is crucial to determine whether we can use individuals from different cohorts to sort of compare their different outcomes. And specifically for patients with more recombinant forms in Africa that are very diverse from those individuals in the other populations, this is difficult. Whereas for certain subtypes C patients with certain kinds of genetic variants, transfer is indeed possible and meaningful. We also learn when to transfer if similar patterns exist in the well-curated data set. And this information is basically based on how similar the viral loads are of the individuals, the distances between the patients, as well as their strains. So if this is interesting, please come talk to me at the poster session, and I'd be happy to share more. Thank you.
Thank you, Sonali. And now on to our next speaker, Kalisha Bullard. She is a postdoctoral researcher at Facebook Artificial Intelligence Research. Kalisha?
Okay, so my name is Kalisha Bullard. I am a postdoc at Facebook AI Research, and I'm going to talk to you today about some recent work I've been doing on emergent communication for embodied multi-agent populations. So this will be a little bit different from the talks we've heard prior because it won't focus on the healthcare domain, but it will focus on artificial intelligence. Okay, so imagine you had all of these embodied agents existing within one and operating within one shared environment. So this is famous roboticist Maya Matarik and her social robots. And you can imagine in the future, we'll have these human robot systems where you have robots and humans that need to operate in tandem. So one question could be, how could these agents learn to communicate in order to aid in coordination? And one might think, well, what if you had a data set that you could use in order to train the agents to communicate. However, each of these agents actually have slightly different embodiment, and you would need large data sets in order for each of these agents to learn how to communicate, particularly to communicate a wide range of different intents. So also, even if you could train the agent through supervised learning, there's the question of what if an unforeseen event happens like a pandemic, and this completely changes how people and artificial agents need to communicate, so they need to change their protocol. So the nice thing is that something like multi-agent reinforcement learning provides an opportunity to allow agents to learn a protocol through agent-agent interactions without the need for huge existing data sets for each agent. So, so this work is, the motivating research question is, how do we emerge generalizable nonverbal communication skills for embodied agents? And it's motivated by the idea that humans inherently communicate through movement. And so we want to enable, if we want to get towards general intelligence, we want to enable artificial agents to do the same. So the problem settings that we have agents play a cooperative referential game where the goal is for a receiving agent to interpret what a sender is referring to. So here you have a sender that's embodied. It will get a batch of communicative intents. It will generate messages in the form of motion trajectories. A receiving agent will try to predict the intent being communicated, and then the loss is back propagated. In this problem setting, however, one key challenge is that when you have a high dimensional continuous channel like motion and self-play, you have a highly non-convex optimization landscape, which means you have a lot of local optima, a lot of different ways agents can converge on a communication protocol. So you want to constrain the protocols they emerge on in such a way where they have similar properties. So the question is, under what realistic minimal common knowledge constraints can we obtain zero-shot coordination, which is generalization of the communication protocol? We take two assumptions from realistic settings. One is that there's a physical cost to energy exertion, and we can exploit that and have agents try to minimize their energy exertion. And the other is that in realistic settings, all communicative intents don't occur at the same frequency. So we can incentivize agents to drive down energy most for the intents that occur at the highest frequency. So just I'm going to show you one result here. It's a qualitative analysis where here's a learned policy for one agent in the population. It was trying to communicate two different intents. And what we see is by the end of the communication protocol training, the agent is able to learn a protocol that completely decouples the specific way that it communicates from the intent being communicated. So here, the blue curve represents intent 1, orange intent 2, which means that based upon just the energy exertion, a new agent could predict what the agent is trying to communicate. And we see in terms of zero-shot coordination, the red result means that with almost perfect accuracy, a new agent can predict the intent based upon the energy distribution. So this finding tells us that we can enable agents to learn to communicate effectively through agent-agent interaction, such as they can communicate even with novel partners at test time. So if this is interesting, please visit my poster for more information.
Thank you, Kalisha. And now on to our final lightning talk from Kina Saucolo, who is a PhD candidate in computer science at Cornell University.
Okay, great. So hi, everybody. I am Kina Saucolo. I'm a third-year PhD student in computer science at Cornell, and I'll talk a bit about my work to understand the role of AI-enabled healthcare throughout the Global South. All right. So recent advances in AI have increased the potential for AI applications to transform healthcare throughout the Global South. However, as researchers and large technology companies rush in to develop AI applications that aid the health of marginalized communities, it's critical to consider the needs and perceptions of community health workers, also known as CHWs, and other stakeholders involved in integrating these AI-powered applications into the essential healthcare services provided to low resource and rural communities. Additionally, as the lack of AI policies within the Global South leaves room for something called algorithmic colonization by these outside entities, structures that guide the use of AI will ensure that these technologies cause no harm to populations they intend to help. So my work has pretty much been split up into 3 parts. And so I first started off with a virtual fieldwork study I conducted over this past summer in India, in rural India. It was in, can't remember the exact place, sorry. And so we conducted an empirical study examining community health worker perceptions of AI. And so from that, we we interviewed around 21 practitioners who work as community health workers. They were all women because they're generally women in that context. And so we gauged their knowledge of AI, which actually proved to be a bit low. And in that study, we actually presented a demo of how an AI app would work and try to, gauge your perceptions of the acceptability and also like feasibility of AI. And we got some very interesting results in terms of, potential job replacement, which kind of goes into the theme of automation of AI, and then also perspectives about how the patients would feel about using AI. And next, I've gone into like a deeper literature review, trying to like analyze more deployments of AI-enabled health tools in these kind of contexts. And so honestly, there haven't been that many. There's a significant one, an AI deployment from Google Health, and it actually did not go so well. And so this kind of backs up my work, trying to kind of, go into the field first to see whether or not like, AI is actually feasible within these respective contexts. And then third, I've been working on developing a framework called ASIPS to understand how AI is introduced on patients, whether or not they're in the global South or the global North, and trying to understand the challenges that this introduction poses on the relationships between providers and patients, focusing a bit more on how patients perceive AI and how they accept AI. And so if any of this is interesting to you, please feel free to visit my poster. It's F8. Thank you.
Thank you, Chinasa. And a big thank you to all of our lightning speakers. Please check out their posters during the poster session when they will be available to answer questions.